Hello, and welcome back to reactor heat transfer. At this point, we're going to start talking about models for convection coefficients in ducts and tubes. So when you have flow inside of an object. We're going to start with round tubes or pipes, and we're going to solve the energy equation. So if we have U dt dx, which is our x direction part of the energy equation, in laminar flow we can solve U, and we come up with this equation right here. So we have U dt dx. Here's our equation for U. Here's the equation for dt dx, and here's our conduction through the fluid in the radial direction. So if we have a constant surface heat flux, then we can say that dt dr is going to be constant at the surface. And what we end up achieving after going through and solving this equation based on that boundary condition is that the Nusselt number is equal to 48 over 11, which is approximately 4.36. We actually get a different result if we assume a constant surface temperature, because the temperature gradient is no longer a constant, but the temperature itself at the surface is. And that gives us a slightly smaller Nusselt number of about 3.66 based on the hydraulic diameter for both of these cases. Now, both of these analyses assume fully developed flow, so it's important to note here that the Nusselt number is constant because fully developed flow has been assumed and the shape of the temperature profile remains constant. Now, at that point, the Reynolds number and Prandtl number no longer have an impact because, again, those profiles are constant. Now, there is also a large number of other possible laminar flow geometries: square ducts, rectangular ducts, infinite parallel plates, triangular ducts, and we can actually come up with Nusselt numbers for both uniform heat flux and uniform temperatures and friction factors for laminar flows in all of these geometries, and you can see them here in the table. Now, we'll need to modify this for the entrance region. Now, there's different ways to handle this. A very common one is to use the Grates number, which is a modified form of the Peclet number that accounts for the length to diameter ratio. So you can look at these graphs and kind of see how the Nusselt number changes for laminar flow in a pipe, depending on the Grates number or the entrance length. Now, the simplest case here is for a fully developed velocity profile. The assumption there is that the velocity boundary layer develops much more quickly than the thermal boundary layer, and so the entire system can be assumed to be fully developed in terms of velocity, even while the thermal boundary layer is developing. So that gives you only for a thermal entry length or for a combined entry length where they're both developing together. Depends whether that case is valid, that fully developed velocity profile, depends on the Prandtl number. If we want to extend to turbulent flow in ducts, we have to be a little bit more careful. We can't come up with these solutions analytically, obviously. So we can use the momentum heat transfer analogy. If we assume that the Prandtl number is 1, then we can actually use that dimensional analysis and analogy to come up with the Stanton number is equal to friction factor over 8, which we can then convert, if we have a friction factor model, to a Nusselt number correlation. So again, this requires that Prandtl number is equal to 1, so it's limited in terms of use, but it does provide some information, because the heat transfer coefficient is related to velocity to the 0.8, diameter to the negative 0.2, it's linearly related to thermal conductivity, and it's related to the momentum diffusivity to the negative 0.8. So for a given flow rate, increasing diameter will also decrease the velocity because you're specifying a mass flow. So if you increase the flow area, the velocity is going to decrease. And when that happens, the value of h will decrease. So small tubes with very high velocities will give you the highest heat transfer coefficient. This is useful, but it's also a problem because those small tubes with high velocities also have the largest pressure losses which means you'll require large pump power. So there's an engineering optimization problem here between optimizing the heat transfer and optimizing the friction losses. As far as empirical correlations that try to account for variations in Prandtl number, the Dittus-Belter correlation is probably one of the most widely used correlations for tubes and ducts. Here you can see that the value of the Prandtl number power is going to change depending on whether the fluid is being heated or cooled. 0.4 for heating, 0.3 for cooling. And this is pretty much valid within 25% error, so 25% uncertainty, for a range of Prandtl numbers from 0.5 to just over 100, and for Reynolds numbers from 6,000 to about 10 to the 7th. It's also limited to fully developed flows within relatively smooth pipes that don't have much roughness. Now, I should also note here that in turbulent flow, the heat transfer is no longer governed by conduction, it's really governed by the turbulent mixing in the flow. And so, for turbulent flows, you're not going to see separate correlations for the constant temperature and the constant heat flux boundaries. They'll be almost identical. So typically we model them both together in a single correlation for turbulent flows. Now, we can also look at the Sider and Tate correlation. If the temperature differences are quite large, you need to account for the difference in surface fluid properties. So we need to make that adjustment. In rough tubes, turbulence is going to be enhanced. The heat transfer coefficient is actually going to be increased. Now, if that's the case, the Dittus-Belter and the Sider-Tate correlations, which assume smooth pipes, actually are going to underpredict the heat transfer by between 5 and 15%. So we need to use a little bit of a variation, the Nielski correlation or the Pedikov correlation. And here, these are based on the momentum heat transfer analogy with some modifications. So you can see that friction factor over 8 for the Nusselt number behavior. And then there's also this K parameter. So in the Nielski correlation, it changes for liquids and gases. But so there's some empirical parameters that need to be dealt with here. It's also important to note that the Nielski correlation also accounts for entrance length effect when calculating the average heat transfer coefficient. Here you have the entrance length effect built into it. We have to be very careful when selecting which correlation we want to use for a particular problem. There have been many correlations developed over many decades of research, and sometimes it can be difficult to choose between the two. For flow inside channels, the Dittus-Belter correlation is pretty reasonable if you need to have a quick solution with pretty reasonable accuracy. It doesn't have to be perfect, but it should be at least within order of magnitude correct. If you want to do a more precise calculation, then you should be looking at the Nielski or the Pedikov correlation if you're looking at some final design ideas or something of that nature. So be careful. Be aware of the limits of these correlations. Make sure you're within the range of conditions they're applicable for. And just pay attention to the definition of the Nusselt number, the length scale, which is typically going to be the hydraulic diameter.